In question 2, we're going to do a hypothesis test for a single variance. Now, we're going to assume the standard deviation of female weekly earnings is a constant $61. And it's been like that because it's been like that for decades. It's been fairly consistent for, decades. And what you're interested in to find out is whether there's a difference in the variance of female, which we're holding constant $61. We're assuming we know the sigma squared for females is $61. We want to know if the male variance equals that $61. So to test this, you sample 28 males, which provides a sample standard deviation of 63.2. Now, notice that the null hypothesis here and the alternative hypothesis begin with sigma squared. Well, the sample standard deviation is 63.2. Up here, we're assuming the population standard deviation is $61. So, when we choose the option for the null and the alternative hypothesis, we have to square the $61. So anywhere down here where you see 61, you do not choose those. And 61 squared is 3721. So we're going to be choosing one of these that ends in 3721. Now, if you come back up here, again, remember the variance of female is some known, maybe the Greek gods have shined down upon us from above and have said sigma squared for females is $61. Or sigma for females is $61. So, and we want to know if there's a difference between that variance of 61 squared and the male variance. So that's that right there, the difference. That's just that this is a two-tailed test. So for the alternative hypothesis, we're going to choose not equal to 3721. Again, 3721 is 61 squared. Okay, so this right here is the alternative hypothesis. What's the opposite of that? Equal to. So for the null hypothesis, we're going to pick equal to 61 squared. Now, with alpha equal to 0.02, we want to determine the critical values of this test. So alpha divided by 2 is the significance. So I'm going to copy that. Also note that this is a two-tailed test. Not equal to is the same thing as less than or greater than. So this is a two-tailed test. We have to divide the alpha by 2. So significance. Actually, I'm going to write alpha equal to So significance level is equal to 0.02. Alpha divided by 2, because it's a two-tailed test, we have to divide the alpha by 2. The alpha divided by 2 is 0.01. Okay, now we need to copy some other stuff into Excel. The sample size is 28 males, and that yielded a standard deviation of 63.2. That standard deviation is the sample standard deviation. So my n here is equal to 28. The degrees of freedom is 27. The sample standard deviation was 63.2. The sample variance is the square of the standard deviation. In part B, we have to determine what the critical values are. Now remember, this is a two-tailed test. So, if this is a two-tailed test, enter the value of the lower critical value in the left answer blank and enter the upper critical value in the right answer blank. The critical values are found in the row corresponding to the degrees of freedom of the chi-square table. Now, because my chi-square table is more intuitive, we're going to use it instead of the book's chi-square table. And the reason my chi-square table is more intuitive is because if the two-tailed null hypothesis is true, then sigma squared is going to be equal to this value. Because the sample variance is going to hover near the true population variance, sigma squared. We expect this S squared divided by this number here, we expect that ratio to be close to 1. So a number that is close to 1 times n minus 1 is going to be close to n minus 1. So if a two-tailed null hypothesis is true, chi-square stat should be around n minus 1. So now we're going to open up my chi-square table. And you open it, the columns are color coordinated. Okay. So I have the degrees of freedom down the middle too. Why do I do that? Because the degrees of freedom is the center, or is associated with the hump of the distribution, the chi-square distribution. These values over here are all lower critical values. These values are all lower or smaller than the degrees of freedom. So these values over on this side of my table are lower critical values. The values up here are upper critical values. So if my significance level is 0.02 and it's a two-tailed test, I divide the 0.02 by 2, I get 0.01. So I start in this column and I go down until I get to the degrees of freedom, or degrees of freedom 27. So my upper critical value is 46.963, and I go down until I get to the same color column. So my lower critical value is 12.879. My upper critical value is 46.963. I'm going to go ahead and copy those values, and I'm going to paste in my Excel worksheet for this problem. So this right here is my lower critical value, and this is my upper critical value. Go back to Cengage now. I have this value and I got this value, and both have to be in 3 decimals. So let me change it to 3 decimals. Highlight them and then shrink to 3 decimals. I'm going to copy the first one and paste that into Cengage now. Then I'm going to copy the second one and paste that into Cengage now. In part C, we have to compute the test statistic to 4 decimal places. So I'm going to open Excel back up. Notice the test statistic is the degrees of freedom times the sample variance divided by the hypothesized value. Remember that sample variance is the square of the sample standard deviation, and the hypothesized variance here is the square of the assumed value of the female standard deviation, 61. So, moving on, the test statistic, I'll call it test stat. It equals the degrees of freedom, in this case 27, times the sample variance for males, and then we divide that by the hypothesized male variance, which equals, in this case, the pretty steady female variance over the last few decades. So the test statistic is 28.98266. Reduce it to 4 decimals, and we paste it into Cengage Now. Now I'm going to go ahead and double check my work, see if everything so far is correct. It should be, and it is. So, is my test statistic in between the critical values? If it is in between the critical values, then the difference between the male variance and its hypothesized value is insignificant, and that is the case here. So we have evidence in support of the null. And for that reason, the null cannot be rejected. And then check my work, and we should have all the problems done correctly. And we do.